Okay, so last time we were talking about the chain rule, and we're going to pick up now with some stuff that's not in the book, but let me remind you, the book is not the definition of what's fair game for the course, right? So there's this thing called the content syllabus that defines what's fair game for the course. And the idea is you start with what's in the book in the given sections. No, wrong one. There we go. And then subtract from that the stuff that's in the excluded material column, but then add to that the stuff that's in the included material column. And one of the things that is in the included material is second derivatives for the chain rule. So that's what we're going to talk about today. It's ultimately not that big a deal. You just have to be careful and interpret things appropriately. And specifically, remember, if you have a function of x and y, say z, for example, is a function of x and y, then its partials are also functions of x and y. That's going to end up being the big trick right here. If you have a function of x and y, so are its partials. Now, how that shows up in the process we're going to see as we go along, I think this is best understood by just diving in and doing an example, and I think you'll get the hang of it. So here we go. We've got z as a function of x and y. Notice I have that indicated on my diagram as we've been doing. And then in addition to that, I've got r and theta being the usual polar coordinates, and so that means x and y are functions of r and theta also in the usual way, right? X is r cosine theta, all that stuff. Okay. So this being the setup, we've got our diagram for use with the chain rule. We've been asked to compute a second partial with respect to r, the first step of which, of course, is going to be to compute the first partial with respect to r. Okay. All right. So now slowly and carefully, again, is the key. We've got, want to take the partial of z with respect to r. And so there they are in the diagram. We have two paths and thus two terms as indicated here, right? This is regular old plain old chain rule. Nothing tricky's happened yet. And what I am going to do, though, is rewrite this a little bit because we actually do know a few things about what we have in this story here. Partial of x with respect to r, for example. Well, we know what x is. X is r cosine theta. Easy formula. So partial with respect to r is just cosine theta, right? And then likewise, partial of y with respect to r is sine theta. And then a couple of notational points. This partial of z with respect to x, just as a notational choice, I'm going to write that as z sub x because it makes it look a little bit more compact. Okay, likewise here. Okay, so now, next, I want to take this partial of z with respect to r that we just computed. And in order to compute the second partial I was asked to compute, notice I'm just going to then take just the r partial of the existing r partial that I already have. Okay? Okay. All right. And a couple of parts of this are no big deal. Now keep in mind, again, we already have that. So let me just substitute in what we already know for partial of z with respect to r. And a couple of easy observations. If I'm taking a partial with respect to r, don't forget that that means that theta is a constant. That's the rule for partial derivatives. All the other variables are held constant. So theta is a constant. That means that cosine theta is a constant. Sine theta is a constant. And so I can sort of, if you will, factor out those constants right there. Is everybody with me so far? And here's where it gets a little bit tricky. This is the heads up part of the problem. I find myself looking at now taking a partial of zx with respect to r. And keep in mind, we don't yet have this new diagram, so pretend like you can't see that just for dramatic effect. Right? Partial of zx with respect to r, we're looking just at this diagram for the moment. And, well, golly, where is zx on this diagram? It's not here. I don't see it, and so it's hard to figure. What do you do with this? How do I treat partial of zx with respect to r? So back up to the very top of the page, and remember what we said at the very beginning. If z is a function of x and y, so are its partials. So zx is a function of x and y, and just note that on your diagram. And that's all I've got here. Zx, function of x and y. So I explicitly add it right there on the diagram. And now I can see how it fits in with other things. I can see how it relates to these other variables. Ditto for zy, by the way, also a function of x and y. And so now, with this diagram appropriately appended, I can ask again now, what is partial of zx? Oh, here it is. There's zx. What's its partial with respect to r? Oh, well, there's r. And the diagram tells me exactly what to do. I have two paths between those variables, and that gives me two terms in my chain rule. So how are we doing? Is everybody with me? So what I've done there is I've rewritten this partial using the chain rule per the diagram to get that. Notice that I've left this constant, like you should for any constant. I've left it there as a factor. Right? We'll get to the second term over here, this zy business. We'll get to that in a minute. But for that first term, is everybody happy? So you see, there's really nothing to it. You just have to recognize what these partials are as functions, and then again, just follow the diagram. Let the diagram be your guide, and it'll tell you what to do. In particular, it's what told us how to do what we have in yellow over here to rewrite that partial with the chain rule. Okay, and then you can probably see this coming. We're going to do practically the same thing for the other side over here. Partial of zy, there's zy, with respect to r. There's r. Again, I have two paths, one by way of x, one by way of y. So I have an x term and a y term, thus turning that into that. And again, this constant sine theta stays along for the ride. Anybody good? So it's kind of all over with the shouting at this point. Maybe a little bit of notation, a little bit of simplifying, but the work is all done. And here we go. Don't forget partial of zx with I shouldn't do that in gray. Partial of zx with respect to x is just zxx. Right? Z is directly a function of x. There's no sort of chain rule to be done there. There's no intermediate variable, so it is what it is. Partial of x with respect to r, again, cosine theta. A little simplification, just like we did before. Again, notation, easy derivative, constant, notation, easy derivative, et cetera, right? It's all the same ideas. And then you can kind of multiply this out and collect terms, and this is your final simplified answer. Okay, everybody on board? All right. Okay, so the big advice that I'm going to give on questions like this, a couple of things. First of all, make sure that when you take a partial and thus new variables appear, make sure to add them to your diagram so that you can see explicitly in your diagram where they come from, what they relate to, and how the chain rule might be necessary at some point. Right? The second advice I'm going to give on this is don't do these too quickly. Don't try to do too much in your head. It's easy to. I was doing 3 steps at once to try to save some ink, and I forgot about the, whatever it might happen to be. Really easy to make mistakes there. So nice and slow. Notice, for example, I took the time to go ahead and recopy that. I took the time to go ahead and factor out these constants, and only then did I stretch these out, and then only after that did I start rewriting what those things are. So one step at a time. Don't get in a rush. Okay, now let me show you an application of this. This is going to involve a very important thing, very important operator called the Laplacian operator. This is a really big deal in, a lot of physics and engineering. The Laplacian is one of the main tools for talking about the heat equation. If you want to know how heat flows, heavily relies on the Laplacian. How waves propagate, heavily relies on the Laplacian, and much more. So here it is. This is the formula for the Laplacian. It's an operator. It's a bunch of derivatives to be taken of whatever you're applying the Laplacian to. And why the Laplacian is so useful in physics, I'm going to leave that to physics and engineering professors to flesh out. But anyway, so what we're going to do is try to understand it differently in this class. And in my old days, past life as a second major in physics, I used this formula a bazillion times. This is also the Laplacian. You'll notice. Same notation, it's the same thing. This is the exact same thing, but in spherical coordinates. Now, where did that come from? It basically came from the second derivative chain rule that we talked about on the previous page. So specifically, for example, you take this right here, second partial with respect to theta. Second partial of f with respect to theta. Well, you can compute that much like we did the second partial with respect to r, right here. You gotta have a diagram and just slowly and carefully, and takes a little bit, right? It's a little bit of effort, but you can totally crank out what this is. And likewise, you can totally crank out that. And likewise, you can totally crank out that phi partial of what's in the inside there. And likewise this, and likewise that. It's work, right? It does take some time to do. But having done it, plug them all in, you can confirm that this is what the Laplacian looks like in spherical coordinates. I'm not going to go so far as to suggest that you actually do it yourself, because it is a lot of tedium. Okay, so second question after understanding where this comes from is, why would I ever choose to use this much uglier seeming thing as opposed to this much more attractive looking thing, right? Why? What's the advantage of the spherical Laplacian? Well, let me show you in an explicit example that comes from an actual physics problem. So, if you want to understand gravitational potential energy, electric potential energy, how electrons behave in the vicinity of other charges, this kind of thing, turns out this is one of the big deals. You need the Laplacian to equal to 0. Laplacian of the potential is 0. Okay, so let's test a candidate possible electric potential on the basis of whether it satisfies this equation right here or not. And here it is, 1 over rho. What constant? Feel free to throw a constant k in there, whatever you want. But 1 over rho is the candidate we're going to consider. And by the way, it turns out this is valid. This works. Okay, so notice I've written it in spherical coordinates. Why? Because, it's easier to write down in spherical coordinates. Look what it looks like in rectangular coordinates. Not that it's all that horrible, I suppose, but it does have a square root involved. There are 3 different variables visible, as opposed to only one spherical variable. So a little bit uglier, but at this stage, perhaps not so persuasive that rectangular coordinates is bad here. But let me point out, even though it's not that bad, there's good reason for us to think that this calculation should be better in spherical coordinates. And that is because if you look at a charged particle, for example, and the potential that's created by a charged particle, or the gravitational potential created by a mass, you would expect it to be simple in spherical coordinates. It only depends on distance. It only depends on rho. It should only depend on rho. It's extremely natural. It's a function of only one variable. It's constant with respect to the other 2 spherical variables. Spherical coordinates should be awesome, right? So let's consider our options then. How are we going to go about computing what we're supposed to compute here? Well, for the Laplacian, you can either use the rectangular Laplacian or you can use the spherical Laplacian. And again, at this stage, I recognize totally rectangular is looking better so far. Right? The game's not over yet. Whichever I choose, I'm going to have to apply the function written in the same coordinate system. And now, let's start thinking in terms of how would I actually compute this. How would I compute, for example, this thing right here? Well, I'm going to have to start taking partials of an expression that has a square root in the denominator. Right? And this is it's going to be annoying. It's going to be tedious. And by the way, everyone should do this once in their lives, if only to say that they did, and I've done mine, and it's your turn now. Right? So, it's going to take you a page, or at least. And this is just a suggestion, you don't have to. But it's a healthy exercise in experiencing what wouldn't it be nice if I never had to do that ever again. So anyway, a lot of annoying details. All right, here's the other option. I could do this. Can crank this out. Now this looks much worse, doesn't it? But look how easy it actually is. Rho partial of 1 over rho, negative 1 over rho squared, which when I multiply by rho squared gives me a constant, and when I take a derivative of a constant I get 0. So this first term, threatening though it looks to be, that first term is just 0 as it applies to this naturally spherical function. Right, so this is the kind of good news that you get to capitalize on. Next, looking at this second term, I need to take the phi partial of that thing, 0. There's no phis in here. We're done. This whole thing, poof, goes away. Gotta love it. And then, lastly, this term, I need to take the theta partial of this thing that has no thetas in it. Again, 0, poof, whole term goes away, and we're done. We have confirmed that Laplacian is indeed 0. Way easier calculation than using rectangular coordinates. And the thing that made this possible is the ability to rewrite the rectangular Laplacian as the spherical Laplacian, which was possible because of the chain rule, second derivative chain rule applied to this diagram, like on the previous page. So, really important stuff in physics and engineering, and big advantages per down here. How we doing? Everybody on board? Okay. Alrighty. So, moving along. So, this next section is about something called directional derivatives. What I'm going to do here is I'm going to start off by reminding us of what are partial derivatives and also kind of rephrasing how we think about them a little bit. So, first thing we know about partial derivatives, by the way, this is for a differentiable function. Keep things convenient. Partial derivative, it's the slope of the graph. In the appropriate direction, of course. So let me keep it simple. It's the slope of the graph. It is also a multiplicative factor. It's what you multiply by input change to get output change. As you all know, one of my big points of view about derivatives is that it's a relationship of some sort appropriate to the context. There's some sort of a relationship between input changes and output changes. And partial derivatives make that relationship in the form of being a multiplicative factor. Okay. Next, now this is a rewrite, but still we're talking about partial derivatives. I claim you can take the definition that we started with for partial derivatives, and you can rewrite it as this, which at a glance looks pretty different, but keep in mind, if you're at a point A, right, the act of adding t times ei, and then you start looking at coordinates, only the ith coordinate gets anything added to it, right? All of the other coordinates except for this one don't change, aka they remain constant, which is kind of how we define partial derivatives, right? And then having added this t in, just into the ith coordinate, notice we take the derivative with respect to t, the single variable derivative with respect to, effectively then, just that one coordinate. So I hope it's not a tough pitch to claim that this is the definite. This is an alternative definition of partial derivatives. Different way to write it. Okay. And then lastly, now here's another formula that I'm not sure if we've written down before, but you can also use this formula for partial derivatives. An easy sort of confirmation of this is to recall that this gradient is a vector of a bunch of partial derivatives, and when you dot it with EI, just in the dot product, you're just going to get the partial derivative in the ith entry, namely you're going to get the ith partial derivative. Okay, all right, so all of these true facts about partial derivatives. Is everybody on board? Okay. So here's the perspective I want to take on this now. Notice nowhere in what I wrote down here did I say the word coordinate. When we define partial derivatives, we define it in terms of coordinates, right? Do certain things to these input variable coordinates, do a different thing to these other input variable coordinates, etc. But nothing in how I've written it here says anything about coordinates. So, point is, you can think of the partial derivative as being something that you do with vectors. And ultimately, that's a more natural way to talk about things. So coordinates can be useful sometimes, and if it's convenient, go ahead, but you don't have to. There's nothing naturally... Coordinates are an invention that we use for our purposes when they're convenient. So here's an example. Let's take this room. Temperature in this room. That's a function, right? But I can talk about temperature being something I can measure at any given point in the room without setting up a coordinate system at all. I don't have to say that's the x-axis, that's the y-axis, that's the z-axis, and the origin shall be right here. And I don't have to say that. No coordinates at all. You give me a point in this room, we can talk about the temperature there. Completely coordinate free. Right? So that being said, what is it about what I have written here that defines what we mean by this partial derivative? And the answer is it's just this unit vector that tells you which direction are you looking in, or what vector are you using to deviate from where you are, however you want to say it. Right? This one unit vector. And nothing in what's written here, right, in any way relies on the fact that this unit vector is pointing parallel to an axis. Not a thing. Right? Now, so I'm going to make an appeal now. This is not a proof. This is not intended to be rigorous or anything. This is just hopefully you'll buy it. And I think it's pretty intuitively satisfying. Because nothing about the relationship between these concepts relies on this being parallel to an axis. It shouldn't have to be parallel to an axis. The fact that this slope and this factor and the value of this expression and the value of this dot product, the fact that these are all equal to each other, this should be true for all unit vectors. Why not? Now, it's just an intuitive appeal. That's not a proof at all. But with that in mind, I'm going to run with the ball on that and say, hey, you know what? How about that? Why not, indeed? And so here's the statement. Take any unit vector at all. It does have to be a unit vector. But anyway, any unit vector at all. And I'm going to say, I can still write down this expression. I can still write down that expression. I can still talk about what would be the slope of the graph as you move in that direction. I can still talk about what's the multiplicative factor between input changes and output changes as I move in that direction. And we should expect these things all to be equal. After all, they were for these unit vectors, and these unit vectors here are nothing special. Again, coordinates are an optional point of view, right? So that's the intuition, this assertion that I'm making is true. These things indeed are all equal to each other, and this is an interesting quantity because it's basically, this thing as I've got it, these equations that I've got them describing, it's basically a partial derivative, just not in an axis direction, but in an off-axis direction, and but it's like a partial derivative. Other than that. And we have a word for this. It's called the directional derivative. Here's the notation that we use. Notice that the, let's see here, I want to color code here. The unit vector defining which direction I'm going, that unit vector is part of the notation. Right? And there you go. It's called a directional derivative. How we doing? Let me flesh out these with a picture here. This slope of the graph business, etc. So again, previously we talked about partial derivatives. That's what you get when you look in the x direction or in the y direction. And again, as previously argued, there's nothing special about those directions unless you, for whatever reason, feel the need to look in terms of coordinates, which is a highly unnecessary thing. But in absolute terms, there's nothing special about those vectors, those unit vectors. So how about we just pick some other unit vector? Let me see if I can do better than that. Here we go. Pick some other unit vector here. That unit vector defines a direction in which I can take a vertical cross section. That cross section then being a curve, to which I can talk about a tangent line, which I can talk about having a slope. Right? Just not in the x direction, not in the y direction, but in a different direction, the v direction. Right? So in the same way that partial derivatives gives you the slope of the graph, well, ditto, directional derivatives give you slope of the graph. Then likewise, let's see, we've got this business about being a factor. The factor that you multiply by input change. Now, input change could be a discrete movement, a distance that you move in the direction you're going, or it could be a rate of change in the direction that you're talking about going. Input change, then there's correspondingly the output change that you get as a result, and the directional derivative is the factor that you multiply by green to get blue. And so wouldn't it be reasonable, with that in mind, to denote the directional derivative as df ds? Right? Just, in order to kind of make the algebra look good in these two equations right here. So this is a very common second interpretation of directional derivatives. Directional derivatives are df ds. They're the rate of change of the function in question with respect to distance traveled in the direction that you're going. What do you think about that? All right. All right. And by the way, I want to distinguish that from df dt. Right? df dt would say how fast is the function changing per unit time? Here, df ds, it's got nothing to do with time. df ds has never heard of time. df ds, for example, if I'm let's say I'm right here where I am, right? And we've got temperature in this room, and I want to talk about how the temperature changes. I can talk about, as I go through toward that window, right? Hopefully not through. If I go toward that window right there, per inch that I move toward that window, how fast is the temperature increasing? And there's no discussion of time. I don't know. I haven't decided how fast I'm going to go in that direction yet. I haven't even decided that I'm even going to go in that direction, but I'm contemplating, and per inch in that direction, how much does the temperature increase or decrease? Okay. All right. Let's see an example. We've got a function here, and I can ask what's the slope of the graph of that function as I look in a certain direction. And, well, after all, slope of the graph is the directional derivative. I know that from the previous page. This is one of our first interpretations. Slope of the graph is the directional derivative. So all I have to do here is compute this directional derivative, which, by the way, I'm going to do with that dot product formula also from the previous page. Directional derivatives computed by this handy-dandy dot product with the gradient. Right? And so now it's all plug and chug. And it's just details, right? But you've got a perfectly good function right there. If you know the function, you can compute the gradient as formulas. You can plug in the point in question where I'm currently sitting. I can plug in A, x equals 3, y equals 1, plug that right into those formulas. That gives me the gradient as values at the point in question. Now, I've got a dot that, notice, with my unit vector. Notice my unit vector is not given. I'm given just a vector, 3, 4, and the direction I'm supposed to go is, whatever direction that vector is pointing. Well, if I want to claim that slope is a directional derivative, in fact, if I want to make any reference to directional derivative, I need a unit vector pointing in that direction, not just an arbitrary vector pointing in that direction. And so I'm going to have to figure out how to get a unit vector out of this, and no problem, the unit vector is what you get when you take the vector and divide by its own magnitude. Now, in yellow there, I have the unit vector. Also, now just a matter of numbers, and then arithmetic, and done. Is everybody happy? All right. I have a little bit of a language warning, just a heads up, easy mistake to make kind of in a situation here. So we start off at this point, 3, 1. Let's say 3, 1 is right there. It says in the direction of the vector 3, 4. Well, let me say 3, 4 is like that, let's say. I want to go in the direction of that vector. So I want to go, that way as indicated by that vector. But and then of course I had to, take that and divide by the magnitude to get the unit vector pointing in that direction, because that's how we describe directions. So that's kind of what we did. Here's what a student might do due to a misinterpretation, and heads up, please don't misinterpret as follows. When we say the direction of a given vector, this is what I'm talking about. I'm talking about the direction that vector points. Right? Here's the mistake a lot of students will make. A lot of students will say, oh, okay, well, let's see here, 3, 4. I'm going to think of 3, 4 as being a point. Get rid of that mess. 3, 4 as a point might be right there. And in the direction of could be interpreted as toward. Everybody see how you could, if you're casual with the interpretation of the question, you could kind of think, okay, here's 3, 4, and they're saying toward that point, 3, 4. This is the wrong direction. Very importantly, when we say vector, in this case, we literally mean vector. Vectors, keep in mind, are defined by two things. Vectors are defined by a direction and a magnitude. So one of the fundamental defining characteristics of a vector is the direction. That's the direction I mean when I say the direction of. Does that make sense to everybody? So anyway, heads up on this. On an exam, if you're unsure, like if I phrase it a little differently and you're literally unsure which one I meant, ask. I'll be happy to clarify. Right? But this is a potential confusion, so make sure not to accidentally step on that landmine. Yeah.
Why would the red point not be on the green line?
Why would it be?
You said the green line was vector 3, 4, the direction?
So let's see here. So the vector 3, 4 is like this, right? Interpreted as a point. Maybe I think it's the origin. The origin is like over here or something.
Oh.
And so, interpreted as a point. I guess I didn't draw this very well, but interpreted as a point. That same vector interpreted as a point would probably not end up on that line.
Okay.
Yeah.
And we're supposed to think of it as the direction of the vector as going from the origin?
Vectors don't care about the origin. Vectors don't have a location, right? Vectors indicate a direction.
Okay.
Right? It's like, where is north?
Yeah.
There is no location of north. North is a direction. Anywhere you happen to be, there is such a thing as north.
Yeah.
Right? It doesn't itself have a location.
Yeah. Okay.
Is that satisfying?
Yeah, I got you.
Okay. Cool. Okay. So next example. Clean up my mess. There we go. Another temperature example. I like temperature as a example. I find it relatable. We've got a function giving me temperature as a function of location. And as before, I'm at a certain point and I'm moving in a certain direction, or I'm contemplating moving in a certain direction. And I want to know, how fast is the temperature changing per unit distance traveled if I were to move in that direction. Okay? So again, notice there is no statement in here about any actual movement in that direction. So I can't ask, what's my velocity as I move in that direction? How fast am I moving in that direction? I'm not moving at all. I'm just interested in a certain direction of motion. And in that direction, you can talk about rate of change of temperature with respect to distance. Okay, so again, rate of change with respect to distance is one of our primary interpretations of directional derivative. Right? So the question, as much as just directly asks for directional derivative. And again, directional derivatives are computed with this dot product. And so again, I just have to compute the gradient. Okay, so you got to take your function t, and you got to take its gradient, and you got to plug in the point in question. And altogether, that gives you your gradient vector that you then dot with the unit vector defining the direction that you're going. And of course, now be careful with this. It's not whatever vector was actually given, you can't use, because that's probably not, what are the odds? It's probably not a unit vector. And in order to say the word directional derivative, it's got to be a unit vector. So don't forget to unitize, we say normalize, your direction vector. And then arithmetic and answer. Is everybody okay? All right. Okay, I have some bad news, and I apologize. And it's not my fault. There is an inconsistency in the math, in the STEM community, about the usage of the term directional derivative. And now recall, I was very, very explicit here that we need this vector to be a unit vector. And for the purposes of Math 219, unit vector. It's got to be a unit vector for this course. That's the way our book does it, which kind of dictates that that's the way we need to do it, right? But I just want y'all to be aware that in other contexts, in some cases, the unit vector requirement is removed, thus allowing you to talk about directional derivatives. Any vector, unit or non-unit, whatever. So what's the argument there? Why would they do such a thing? If you remove this unit requirement, what's interesting is these two things are still equal to each other. And furthermore, this thing on the left is still of natural interest. Very natural. if I'm at the point A, and let's suppose now that I am moving not just in a direction, but I know the speed, I know the actual velocity as I'm going. I know my velocity is an actual non-unit vector v. Then, well, a plus tv describes my motion in the domain, and this says compute the rate of change of the function as I move with that velocity in the domain. This is a very natural object, even for non-unit vectors. And it is computed by this very handy formula, even for non-unit vectors. So, in these other contexts, this is referred to as a directional derivative. Now, why does our book choose not to define it that way? Well, the cost is, again, when you remove this unit requirement, is no longer the slope of a graph anymore. It's just not. It has to be a unit vector to get that property to be true. Also, being a multiplicative factor, nope, no longer. Right? So you lose some of the cool, convenient, handy interpretations when you remove this unit vector requirement. But you also get a broader application in that the term then applies to all vectors, not just unit vectors. And so do you want the concept to apply more broadly, or do you want the concept to apply more powerfully but narrowly? And it's a pro-con kind of a situation. And in many other contexts, this other choice really does make sense. So anyway, I emphasize for Math 219, back up to here, for our course, unit vector. Got to be a unit vector, and this class only for unit vectors, etc. I mentioned only for sort of cultural purposes. Heads up, outside of Math 219, beware. Right? If someone says the word directional derivative to you, you should stop them and say, wait a minute, now do you mean, which of the two senses do you mean? And get a clarification before you might accidentally assume wrong. Okay. All right. Okay, so a couple of interesting questions that we can ask that turn out to relate to directional derivatives. Here's the first interesting question we're going to ask. Let's suppose you're at some point in the domain of some function. Maybe your function represents, temperature, again, is one of my favorite metaphors for this. So F represents temperature. I'm at the point A. I'm cold. And I want to warm up. And I want to know which way should I be walking to warm up as fast as possible. I don't want to sit there and walk, and it turns out I'm getting colder. No, I wanted to get warmer. And I also don't want to walk, and find out that if I had just gone a different direction, all that walking would have gotten me warmer faster. Right? I want to go in the best possible direction. So, of all possible directions that I might go, I want to know which one of these maximizes the directional derivative. Right? Which of these green unit vectors is going to make the resulting directional derivative as large as possible? Natural question to ask, right? Everybody okay with the question? I'm cold, I want to warm up as fast as I can. Now, another part of the answer, I suppose, is that if you're cold and you want to warm up as fast as possible, don't walk, run. Run as fast as you can. Right? Drive. Get on a bicycle. Whatever. Move as fast as you can. If you're going in a direction where temperature is increasing, the faster you go in that direction, the faster you'll get warmer. Of course. That's a given, though. Right? It remains that still, in addition to moving as fast as I physically or socially, politely can, right? Which direction is the best direction? Okay. So, this direction is referred to in different ways. It's a direction of, now we have to talk about how do you interpret directional derivative. One way to interpret directional derivative is that it's a way of keeping track of how fast the function is increasing. So direction of fastest increase is a pretty natural way to describe the answer that we're looking for here. Of course, directional derivative can also be thought of as giving you slope. And as such, if you want to make that slope as great as possible, that would mean you're looking what direction should I be going so that on the graph it's as steep as possible. And so they say direction of steepest ascent. So these are just two different ways of thinking about the question. For whatever it's worth, by the way, the more common term here is direction of steepest ascent. And I don't prefer that one. The problem with this term, direction of steepest ascent, is it refers to a metaphor of a way of viewing things that might not be accessible. What if you have a function of 3 variables? I can't look at the graph. Steepness, interpreting the directional derivative as a slope, only makes sense if you're looking at a graph. Very often I can't. So this is a kind of a reference to a point of view that might not exist. But no matter how you're looking at the function, direction of fastest increase always makes sense. So I will always, I will always intend to say direction of fastest increase. That said, when I was learning this material for the first time, however many years ago that was, my professor said direction of steepest ascent, and so I got brought up that way. I'm going to probably say direction of steepest ascent a fair amount in this class, and that's probably a good thing. You're going to hear it elsewhere, certainly, also. But anyway, either of these, fine. Okay, so how to answer this question is actually very straightforward. Here's the directional derivative that we want to make as big as possible. Computed with a dot product. Here is a formula for dot products. Old news. Right? And don't forget, the vector in question has to be a unit vector, so its magnitude has to be 1, so that factor I could just throw away. It's just a 1 after all. And so here then is the thing that I want to maximize. I want to make that as big as possible. And keep in mind, I'm talking about being at a point A where the gradient at that point is some vector, and I'm contemplating different scenarios about how I might move away from that point. But as I contemplate all these different possible directions in which I might move from A, I have not yet moved from A. A is fixed. So the gradient, it just is what it is. The gradient depends only on where you are. It doesn't depend on, or even, it's not even aware of the fact that you're looking in other directions. Right? So the gradient here, magnitude of the gradient, that gradient is a great big constant. So in actuality, when it comes down to it, all I really need to do is maximize cosine theta. Cosine theta is, whatever I can do to make cosine theta as big as possible, that's the winning move. And of course, cosine theta is maximized when theta is equal to 0. Theta, don't forget, is the angle between the gradient and the direction of motion. So I want that theta to equal to 0, and if that theta is equal to 0, what that means is, well, I need this angle to be 0. That means I need to be going in the direction that the gradient vector points. So in other words, this picture is kind of wrong. I need to be going that way. The unit vector pointing in the direction of the gradient. Everybody with me? Okay. And then a very quick ending calculation here. So that's the best direction to go. As you go in that direction, how fast is the function changing? So we maximize the directional derivative. What is that maximum directional derivative? And easy calculation. Again, there's the formula for directional derivative. And let's see here. Don't forget, we've already computed that the vector indicating the right direction should be that. And then, let's see here. Gradient dot gradient is magnitude squared. And magnitude squared divided by magnitude is magnitude. So, Nice, easy calculation right there. And I'm out of time, so we'll draw the line right there. A nice, natural place to end it. End of page 41. So be it. See y'all on Wednesday. Hope y'all had